Let's look at LeetCode problem number 2997. Minimum number of operations required to make array XOR equals to k. So first let's understand the question. So in this question we are given an array nums and a positive integer k. So what we can do in an operation is we can flip a bit in any of the element of the array, and if it is 0 then it will be changed to 1, and if it's 1 it will be changed to 0. So what we have to return is the minimum number of such steps or operations required to make the XOR of the array equal to k. Okay, so let's first see an example. So we have nums, which is 2, 1, 3 and 4, and the k here is 1. So first let's see the binary representations. So 2, 1, 3, 4. Binary representation of 2 will be 0, 1, 0. For 1 it will be 0, 0, 1. For 3, 0, 1, 1. And for 4, 1, 0, 0. So if we do their XOR, so our answer would be XORing means if the bits are same then it will be 0. If they are different then that will be 1. So these bits are different, so that will be 1. These are also different, so 1, and then these are same, so 0, 1, 1. And now we will take XOR of them. So now as you can see 0, 1, 1, 0, 1, 1 is same, so we will get 0, 0, 0. Okay, because all of the bits are same. For 4, what we will get is these bits are same but this is different, so 1, 0, 0. So you can also see that this is 0, and 0 XOR any of the number will be the number itself, so that is 4 again, 4 again, that is 1, 0, 0. And now what we have to do here is we have to convert this into our k. So how are we going to do that? So we have to do some operations, that is flip some of its bits. So 1, 0, 0. So now we have to make this XOR equal to our k, that is 1. So its binary representation will be 1 or 0, 0, 1. Okay, so what if we can choose any bit of any number in an operation and flip it? So for example, we have to change this bit, and we have to flip this bit and make it 0, and flip this bit to make it 1. So that will become 0 and it will become 1, and this bit is 0 only, so our answer would be transformed into k. And how can we do that? Is by choosing any of the bits from any of the number, because if we choose any one bit in any of the number, for example if we just flip this bit to 1, so now our XOR will be, these two are different, so that will be 1, then 1 and 0, that will be 1 again, and 1 and 1 now will give us 0. 1 and 1 now will give us 0 because these are same, so this bit will come to become 0. And similarly we can flip any of these bits, and that will be an operation to flip the bit in the result. Okay, so how are we going to proceed towards this problem is that we don't need to worry about choosing the element, which element and which bit is to be changed. What we can do is we can flip a bit in its answer only, that is the XOR of this array. The XOR of this array came out to be 1, 0, 0. Okay, so we can choose any of its bit. Okay, so if we flip this bit, it's equivalent to choosing any one of these bits and flipping them. Okay, so this is basically approach of this problem, and it's a really easy problem. You just have to what you have to do is, step 1, we will calculate XOR. We will make a loop. Using loop you will calculate XOR of the array. Step 2, in step 2 what you will do is you will get the binary representation of XOR and binary representation of our target, this is k also, and now we just have to make them equal. So what we can see from the example is that our binary representation of array XOR came out to be 1, 0, 0, and our binary representation of k was 0, 0, 1. So how can we do that is we can traverse both of them, and if the bit is different we can flip one of the bit from the our XOR, we will flip it to 0, and we will do our operations. Operation will be incremented here as we required one operation here, so now our operation is 1. And then for the next element, these elements are same, so we don't need to do anything. And for this bit, now these both are different, so we will again flip this bit to 1, so that will make our minimum operation 2, and that is the answer of this example test case also. So this is easy, but you have to only handle one case. Okay, you have to handle one case, that is when the length of binary representation of XOR is not equal to the length of binary representation of K. Okay, if that is the case, then how are we going to do it? For example, let's say our XOR is coming out to be 4, so that will be 100, and our K is nothing but let's say K came to be 8, so that will be 100, that will be 4 zeros, that will be 4, and the length of XOR would be just 3. So what we can assume is, we can assume 0 here. That won't make a difference. You can assume any number of zeros in front of the binary representation. And what we will check is, we will check for this part in the length, and then we will see if this is more than length or this is more than length of this K. So what we will do is, if it's 0, then we don't need to do anything. But here our K has 1, so we need to flip it to 1. Okay, and inside it also it would be flipped to 0, because these bits are not same. Okay, now the first function that we have is min operations. So min operations, and it has the vector num and K. So what we will do inside it is, we will calculate the array XOR, and for that let's make a variable int array XOR and initialize it by 0, because XOR of any element with 0 will give that element itself. Then we will traverse the nums, so I in num. What we will do is, array XOR is equals to I XOR array of XOR, just like calculating the sum of array. And we will calculate this XOR now. And now what we need here is the binary representation of both of them. Okay, so for binary representation, we will make a function. Okay, so let's say you can use a string. I'm using here a vector of bool, and let's say this is binary array XOR, and second vector will be vector of bool again, and binary of K. So this function, let's say binary representation BR function, will take the argument as our number, for which we have to calculate the binary representation. Yeah, and now that we have the binary representation of both of them, what we have to do here is, now that we have to count the minimum number of operations, that is the different bits. Okay, so for that what we will do is, make a variable in op is equals to 0, and iterating in index, let's say I is equals to 0, and now we will traverse the both the representations, both the vectors, this and this, simultaneously. So while I is less than binary K dot size and I is less than array XOR size. So what we are going to do here is that, if our binary representation of K and our binary this vector bk is bk of I, this is not binary of K, it should be b of arr XOR. If these bits are same, then we don't need to do anything, we won't find an operation. So what we should check here is, if they are not equal. If they are not equal, then we need to make an operation to switch them. So here we will do op++, and we will move our iterator ahead for the next index. And now you see that this loops handles where the number of bits are same for both of them. Okay, for example, this and this is our binary representation of K. So this loop will take care up to this only, because I will be less than the size of this and I will be the less than of size of this, and both of the conditions needs to be true. Then it will run for the minimum size only. So it will run up to 3 here, that is 0, 1 and 2 here. And now we have to check ahead for this, assuming that here is 0. And if it was reverse case, for example, if a binary array XOR had more element, if it would have more elements and a binary representation of K had less elements, then we would assume here 0, and this first while loop will loop in this array length only. So now what we'll have to do is, we will again check check if whose size is less, and we can do that in a concise way by writing two while loops again. So we will write a while loop while I is less than binary k dot size. So now if this condition is true, what does this means? This means that a binary k dot size has more number of elements than where the I is standing right now. Okay, so we will have to assume that in this case we will assume it is not assumed now, it is sure that our binary k dot size, that is bk dot size, bk dot size must be greater than barr XOR, because this condition is true. That means this this while loop has broken by this XOR condition, not by this condition, not by this condition. So we will traverse this, and if we find that binary arr XOR or yes, bk I plus plus is equals to 1, we will check for this array. Okay, because its size is remaining, and other array we assume that it has ahead zeros. So if it has 1, then that's where we have to make change, because 0 are already present in the second array, so we don't need to worry about zeros. So if that's 1 or true, then we will do op plus plus, and I have done here I plus plus to move the iterator in this line only. Now let's say this condition was false. Okay, if this condition was false, this means that our binary array XOR has more size. This condition is this condition has broken the loop, not this condition. So we will have to write for while loop for it also. So while I is less than b XOR size, then what we will do is we will check if it is 1, that is b XOR I plus plus is equal to 1, then we will do op plus plus. Okay, and now what you can see here is that we have handled all the cases. How? Because if both the array has same size, then it will handle it. If one of the array has more size, then either this loop or this loop will have its condition true, and that loop will run, and that will consider those cases. And finally what we do here is we will return op, that is the minimum number of operation. Okay, and now if you want the binary representation of it as well, I will tell you. Okay, so our next function is vector bool binary representation, because it's going to return a vector of bool. So now what we'll do is first we'll make an answer that is to be returned. So vector bool answer. And if you don't know how binary representation is achieved, so let's see this. For example, I'm taking just an example, if we have to find the binary representation of, let's say, 4. Okay, so now what you do here is, let's say we know that 4's binary representation is 0, 0 and 1. So we will take mod of 2, 4 mod 2, that will give us 0. And now we will divide it by 2. Divided by 2 will give us 2. And now again mod 2, it will give us 0. Now again we will divide it by 2. This will give us 1. Now 1 mod 2 is 1. And if we again divide it by 2, it becomes 0. So we don't do any operations. Let's take another example. Let's take 3. So binary representation of 3 is 0, 1, 1. Okay. So now for 3, or let's say just 1, 1. So what we'll do is 3 mod 2 will give us 1. And then we will divide it by 2. It will give us 1 again. So now 1 mod 2 will give us 1 again. We'll divide it by 2 and it becomes 0. So we don't do any operations. So what you can see here is that these steps are giving us the binary representations in reverse order. Okay, let's take another example. Let's take 5. So 5 has 1, 0, 1. Okay, so for 5, 5 mod 2 will give us 1. We divided by 2, 3. We divided by 2 and we get 2. And 2 mod 2 will give us 0. Okay, then we again divided by 2, we get 1. 1 mod 2 gives 1. And then again we divide it by 2, so 0, and our operation or the steps stops here. So we see that this is also giving us the answer in reverse order. Okay, so now you can take any of the example. Now you know what we have to do here is, first we have to take mod, then divide it by 2, and then move to the next iteration. Okay, so let's do it. We will make a loop here. So while our n, that is this number, is not equal to 0, what we will do is we will take the mod here. So let's say int or bool current is equals to rn, not bool, it should be int mod 2, and then we divide it by 2, so divide equals to 2. Now as we divide it, and we have got an answer in reverse order. Okay, so for 4 it was giving us 0, 0 and 1. So let's say we push it in the vector. So as in the first iteration we will get 0, so answer dot pushback 0, not 0, our current, and this is over. And now we have the representation in reverse order, so our answer would look something like 0, 0 and 1. Okay, so it's reversed. So if you look at my code, I have initialized it I equals to 0, and from there we have started the comparison. So you can also like reverse it and then write the logic here in reverse order, or if here we just have to compare if the bits are equal or not, so the order won't matter. Okay, it's up to you. So without reversing, we will just return here answer. That will be a binary representation. Okay, so that's all for this video. I hope you have understood this problem. I will see you tomorrow.